Okay, thank you for tuning in to watch the video lecture for Chapter 5, which is what we're going to be covering this week. So just a real quick reminder of what we talked about last week in Chapter 4. So in Chapter 4, we introduced the concept of a force and how forces can cause masses to accelerate. We then kind of related those to Newton's three laws. So we introduced Newton's first, second, and third laws. The big one that we took away was from Newton's second law. Newton's second law was that if we have a system of forces acting on a mass and there is a net force acting on that mass, meaning that those forces are not balanced, then we will have an acceleration of that mass, and that acceleration is related to those forces by Newton's second law. F is equal to ma. We also introduced some kind of specific different types of forces, namely we briefly introduced friction, and then we talked about normal force and tension. And this week in Chapter 5, we're going to introduce some new types of forces, some more specific types of forces, and we're going to start analyzing how they can also be applied to systems using Newton's second law and kind of understand how things act in kind of other scenarios. So the big ones we're going to talk about today is we're going to talk about friction and drag, and then we're also going to talk about spring forces. So Chapter 5, the later part of Chapter 5 goes into elasticity and some material properties of solids, which I think is kind of beyond the scope of a college physics course. So I am kind of deleting that section and I'm adding some of my own content, which is going to be spring forces. So instead of looking at elasticity of solid materials, we're going to be looking at springs, and they are actually kind of one in the same. But once again, for this the level of this course, we are going to talk about actual physical springs. So let's jump right into it. Okay, so we briefly talked about friction at the end of last chapter in Chapter 4. We are going to go into quite a bit more information about friction this week when we talk about it. So what is friction? So let me go ahead and hide my camera here. Friction is defined to be a force that opposes relative motion between two surfaces in contact. And it actually only depends on a couple things. One of the most important things it depends on is what two materials are in contact. So let's look at this example that we have here. So we have a wooden crate. We're not entirely sure what this surface that it's resting on is. Let's just say that it's something like concrete. We would have a specific magnitude of friction, which will depend on the fact that the interface is between wood and concrete. Okay, so that's kind of important. So we want to talk about, there are two kind of separate forces of friction, and this is what we're talking about here. So mechanical roughness between the two sources. So if we have, when we look at this wooden crate on a microscopic scale, it is not perfectly flat. It's going to have all of these kind of ridges and bumps in it on a very, very small scale. The same is true for the concrete that it's sitting on. So we have kind of all of these interlocking, almost like puzzle pieces, right? So these puzzle pieces fit together, and if I try to pull this crate to the right as it's shown here, I'm going to have to pull all these peaks up and over these peaks on the concrete. So where right now everything is kind of slotted together nicely, it's going to have to move all that or wear those peaks down in order to pull that crate to the right. The other source that we have for friction is going to be on the microscopic scale, which is going to be actually between the attractive forces between the molecules. Let's start talking about these two sources of friction and kind of what they mean when we talk about mechanical versus molecular interactions between surfaces. So the roughness of the two surfaces is what causes mechanical friction to act. So we kind of showed it in that previous picture. We have another kind of example here. So what we have is we have all of this mechanical roughness between these forces. The other thing that we have to consider is what is the normal force acting in between these forces. So what we have here shown in these two diagrams is we have some examples of what happens when we have a small normal force versus a large normal force. And there's something I want to talk about here because this is kind of counterintuitive when you're talking about friction. So you would think to yourself that friction would depend on the surface area of the two surfaces in contact. So let's go back to here and I can unhide myself. So if we look over here at this box on the right, we would think that if this box was 1 foot by 1 foot versus 2 foot by 2 foot, it's kind of intuitive to think that, hey, that 2 foot by 2 foot box has a bigger surface area than that 1 foot by 1 foot box. So it's going to have more friction than the 1 foot by 1 foot box. But that is actually not the case. And that comes back down to this kind of model that we have of the rough surfaces where they interact. So even though that box, let's just say it's 2 foot by 2 foot, so it's 4 square foot, even though you would say, okay, there's 4 square foot of contact surface, that is not actually accurate. It's because you have all of these kind of peaks and valleys that you would think that, or peaks and valleys, that entire 4 square foot of surface is not in contact with each other. It's just the places where the peaks line up. So the actual contacting surface area is very, very small when compared to the macroscopic or the large overall dimensions of the box. So the actual surface area of contact is incredibly small. It's just a series of points that are contacting at the peaks. But what happens is, and let's say I keep that 2 foot by 2 foot box the same, as I make it heavier and heavier, what actually happens is those peaks where they're interacting start to kind of deform and they squish together. And so you go from this large separation where you have just a couple or a few contact points, and as you squeeze them together, all of a sudden you have a lot more contact points. You have a lot more contact points. It's still very small when compared to the 4 square feet, but you have a lot more locations where all of those points are interacting. So as you increase your normal force, you also increase the force of friction. So when we talk about mechanical friction, there's really two things that we're talking about. We're talking about what material are we using, because that material is going to kind of dictate how rough the surface finish is between those two contacting surfaces. And then what is the normal force acting between those two surfaces? So if we have rough surfaces, high normal force, we're going to have very high frictional force. If we have smooth surfaces, low normal force, we're going to have very small frictional force. So that means that we're going to say that frictional force is going to be proportional to both some kind of indication of the roughness, and it's also going to be proportional to the normal force. The other kind of source of friction that we're going to talk about, and we're just going to talk about it briefly, is the atomic attraction between different types of molecules. So if I have some material that's made of some certain set of molecules, there's a potential that when it interacts with the surface of a different material, that those molecules will be attracted to each other either through, polar interaction or covalent type bonding. So there's a lot of that's more on the chemistry side, but there is some potential that those two surfaces are going to be chemically attracted to each other at a microscopic scale. So once again, we are going to lump. What we do is we kind of lump those two different sources together. So with the normal force, we're saying friction is going to be proportional to the normal force, but the mechanical roughness between two surfaces and then the molecular interaction between those two surfaces, both of those depend on the materials, right? Both of those depend on the materials. So we kind of lump those two terms together, and we'll get to that here in a second. So here I just want to make sure everyone kind of understands, this is a much better kind of the picture of a 3D model, of friction. So if we look at something on a microscopic scale and we look at the interaction between two rough surfaces, we can see that the actual interaction is going to be very, very complex. There's going to be a ton of different contact points, and they're all going to be exerting forces kind of in different directions. So we can say that roughness in and of itself is very, very complex to model and analyze. Another example here is that we can say even for same materials, like for instance here, this is going to be all cast iron, but different surface finishes of cast iron vary wildly. So this is going to be very complex, especially you see this very, very rough finish here can be very, very complex to model. So because friction is so complex, we actually approximate it. We don't calculate the force directly. We approximate it with a model like we talked about in chapter 1. So let's talk about the model for friction that we use. And we use the model that we use is that there is some coefficient times the normal force. So what we do here is we lump all those kind of weird, complex things in together, the difference between two materials, the roughnesses, and then also the molecular interactions, are all get lumped into this kind of slush constant, which we call this the coefficient of friction. Call the coefficient of friction, and then we also have what we call the normal force, and if we multiply these two things together, that's what we come up with the force of friction. So we kind of jumped into, this is the model that we use to model friction. But as you can see from this slide, we actually have two different types of friction that we model. We have what we call static friction and what we call kinetic friction. So static friction occurs when we have no relative movement between the surfaces. That means that the surfaces that are in contact are not moving with any relative velocity between them. So our two contact surfaces are stationary. Right? So that's stationary. So we can say that that static frictional force, remember we talked about in chapter 4, is what we would call a smart force. So in this case, if I know that this block that I'm showing here is static, that means it's not moving. If I apply a 1 pound force to the right, then my frictional force, my static frictional force, is going to be 1 pound. If I apply a 2 pound force to the right, my static frictional force is going to be 2 pounds. It's going to be whatever it needs to be to try to maintain equilibrium up to a maximum value. You can think about this in real life. If I'm pushing on a box, I apply a force, the box doesn't move, I push a little bit harder, the box doesn't move, I push a little bit harder, the box doesn't move, and then I push hard enough, and then all of a sudden the box starts to move, right? So we know from real life world, from our experience working in the real world, that at some point we can overcome that static friction, and when we overcome that static friction, it begins to move. So that maximum value that the static friction can maintain is given by this equation right here. This is going to be our frictional model. Like we said, where the maximum force that static friction can maintain is going to be the coefficient of static friction times the normal force. Coefficient of static friction times the normal force. So what that means in kind of our basic example that we're showing right here is that once our applied force, our externally applied force F, overcomes the maximum frictional force that static friction can maintain, this block will start to accelerate to the right because we will no longer have balanced forces. The force to the right will no longer equal the force to the left. So the force to the right will be greater than the force to the left, meaning that we will have a net force to the right. And we know from Newton's second law that if we have a net force to the right, then we will accelerate that block to the right. Okay, then the other side, the other piece of this puzzle, the other type of friction that we talk about is called kinetic friction. And it's exactly what you would think it would be if static friction meant that there was no relative movement in between movement in between the two surfaces. Then with kinetic friction, there is relative motion between the two surfaces. In this case, if a box is sliding over a surface, or if one object is sliding over a surface, then the magnitude of the kinetic friction, as we have determined, is actually a constant value. It's actually a constant value. But once again, we model it the exact same way that we model static friction. We have some coefficient of friction, and this time we're going to talk about a coefficient of kinetic friction, and it's still multiplied by a normal force, and that gives us the force value of our kinetic friction. Okay, so the other thing that we want to talk about with kinetic friction is what we call a non-conservative force. We are going to talk about that in a lot more detail when we get into work and energy, but what that means is that friction generates waste energy. Friction gets rid of energy that we're adding to the system. And like you say, when you rub your hands together really fast and your hands start to get hot, that is, you're creating heat as a byproduct of friction. So friction will generate waste heat, which will get dispersed into the environment. And once again, this particular model, I just want to talk about this right here, this bullet point right here. This model of kinetic friction only is valid for low relative velocity between the two surfaces. As you get to be really fast with your velocity between the two surfaces, this model begins to break down. Okay, and what I have given for you here, and this will be in your lecture notes as well, is I have the table from the textbook. Here is a bunch of coefficients of friction between different materials. So for instance, we have rubber on dry concrete, rubber on wet concrete, wood on wood, steel on wood, metal on wood. We have a whole bunch of different values here, and you may be asking yourself, well, how did we come up with all of these values? all of these values are determined experimentally. It's how we these values have been determined historically. So empirically over time, physicists and engineers have done lots and lots of experiments, and they determine these coefficients of friction based off of real world experiments. And that way, that incredibly complex system where we have all that mechanical roughness and molecular interaction, all that kind of just goes away. We run a bunch of experiments and we just slush all of that weird kind of tough complex material into a single constant. So we take something that in reality is very complex, but mathematically we make it very easy. Here's what we were talking about with kind of trying to visualize the force of friction. So what we have here, this is a very common graph that you'll see when people talk about friction. This is what happens as, let's say I have this standard kind of block sitting on a flat surface, and I'm applying a force to the right, which is being opposed by a frictional force to the left. What is the value of the frictional force as I increase my value of F? So remember that static friction is a smart force, So whatever value of applied force I have, static friction will match that in order to stop motion and maintain equilibrium. So what we have here is we have this dotted line, which is just the line F is equal to F, where the frictional force is equal to the applied force. So this is just a straight line, and you can see that the value of the frictional force will match the applied force up until it reaches this maximum value. And this maximum value is going to be the coefficient of static friction times the normal force. Then at this point, we begin to have relative motion. All of a sudden, we overcome static friction. This block begins to slide, and our frictional force drops down to this kinetic frictional force, which is our coefficient of kinetic friction times normal force, and it maintains this. At this point, it doesn't matter how large of an external force we apply. The larger it gets, it doesn't matter. Kinetic friction is always going to have a constant value, which we're showing as a horizontal line here. So this is kind of a good way to kind of visualize how the frictional force changes as you increase your applied external force to this kind of simple system right here. Okay, let's jump into a friction example problem. So the problem reads, Steve is dragging a 10-kilogram block on the ground behind him with a rope, and the problem gives us that the coefficient of static friction between the block and the ground is 0.8, and the coefficient of kinetic friction is 0.6. The rope makes a 30-degree angle with the floor. What tension is required to make the block start moving? Once moving, how much tension is required to keep moving? So this problem is asking us to evaluate two different scenarios here. The first scenario is the block is initially at rest, and we have to overcome that static frictional force. So because the block is stationary, we have to overcome that maximum static frictional force in order to get that block to start moving. However, once it starts sliding and that kind of material interface between the surfaces of the block and the ground start to break down a little bit, it actually becomes easier to move. So the coefficient of kinetic friction is lower than the coefficient of static friction. So once that block starts moving, it becomes easier to move, and we need a smaller force in order to keep it moving. But let's go ahead and jump into the first part of the problem. And the first part of the problem is where the box is stationary. So anytime that we're working on a problem in which we have a mass and we are applying forces to that mass, we are always going to start by drawing a free body diagram. So let's go ahead and draw ourselves a free body diagram for this particular box. So the box is sitting here, and I can kind of draw a short picture as it was given in the problem. So the box is sitting on the ground, and it's being pulled by a rope, and it gave us that the angle with that rope was going to be 30 degrees with the horizontal. Okay, so now this is kind of our problem picture. Let's go ahead and draw ourselves a free body diagram. So once again, we have our mass. Our mass was given to be 10 kilograms. Now we have to consider what forces that we have acting on this system. Well, we have a handful. First things that we always know, if we're working on the surface of the earth, we're working somewhere where gravity is present, we're always going to have the weight of the box that we have to consider. So we're going to have the weight of the box that we have to consider, and the weight of the box is going to be equal to the mass times the gravity or acceleration due to gravity, which is going to be equal to 10 kilograms times 9.81 meters per second squared. In Physics 1, we just round that to 9.8. So 9.8 meters per second squared. That is going to be our weight acting downward. Now, the block is sitting on the ground. And anytime that we have a block or a mass sitting on a surface, anytime that there's two masses in contact with each other or two surfaces in contact with each other, we have a normal force. So we are going to have a normal force acting upwards. Then we know that we have the tension from the rope, which is also going to be applied to this block. So we know that we have a tension acting from the rope in this direction because we're pulling it, and it was given that the rope was at a 30-degree angle. So this tension is going to act along the length of the medium, so we know that this force is going to act with a 30-degree angle as well. Okay, and finally, the last force that we have to consider is going to be our frictional force. So we're going to have a frictional force that opposes the motion between the block and the ground. So if I'm pulling on it with a rope to the right, that friction is going to oppose that motion to the right, and our frictional force is going to be to the left. That frictional force is going to be to the left. But we know more about this frictional force than just that it exists, right? We know that in the initial case where this block is stationary, if we want to overcome our frictional force in order to get this block to move, we know the value of our frictional force is going to be our coefficient of static friction times our normal force. Our coefficient of static friction times our normal force. So now we have a pretty good free body diagram. Okay, to solve this kind of problem, we're going to consider the instant in time, the one instant in time right before the block starts to move. So right when we get to the point where that block starts to move, at that exact instance, we are on the very edge of moving, but we are still not moving. So we still have zero acceleration right before the block starts to move. So if we have zero acceleration, we can say that this block is in static equilibrium. And we said that if an object is in static equilibrium, recall, going back to Newton's second law, we said that Newton's second law is going to be that the sum of our forces acting on a mass is going to be equal to the mass times the acceleration of that mass. If the acceleration of that mass is equal to zero, then the sum of our forces acting on the system is also equal to zero. Okay, but this is important because this is a vector equation. Which means it's not just in one dimension. It can be in 2 or 3 dimensions. This problem simplifies into a 2-dimensional problem. So if we are in a 2-dimensional scenario, this vector equation splits into 2 separate equations. It splits into 2 equations. We have that the sum of our forces in the x direction must be equal to 0, and we have that the sum of our forces in the y direction must be equal to 0. So these are going to be our starting points for solving this problem. These are going to be our equilibrium equations, which we are going to use then to solve this situation. But we have to go and we have to consider what forces that we have acting in the x direction and what forces that we have acting in the y direction. So if we go back to our free body diagram, some of them are pretty easy. Our weight and our normal force are both acting only in the y direction. Our friction is acting only in the x direction. However, our tension is acting in both the x and the y direction. So we have to split this up into components. We split it up into components so that we have a horizontal component of our friction and we have a vertical component of our friction. So we have a horizontal component of our friction, which I can call this tension sub x, and we have tension sub y in the y direction. Okay, now that we understand that, we can go ahead and let's start filling out what forces that we have working on this system. So let me erase this to get a little bit more room. So let's start with the sum of our forces acting in the x direction must be equal to 0. What do we have acting in the x direction? Well, we have our force of friction, which is our coefficient of static friction times our normal force acting to the left. And if I define my coordinate system to be a standard coordinate system with positive x to the right and positive y upwards, that is a negative value. So I get a negative coefficient of static friction times our normal force, negative because it's to the left. And then I also have a T sub x, our horizontal component of our tension, which is going to be plus a T cosine of 30 degrees is going to be equal to 0. And this is going to be our first equilibrium equation that we have to consider for this problem. Now, we're after tension in the rope. That's what the problem is asking for. The problem is asking for tension in the rope, but you can see that this equation also has a normal force in it, which we also don't know. So we only have one equation, but we have two unknowns. So we have to consider our second equilibrium equation, which is that the sum of our forces in the y direction is equal to 0. And we do the exact same thing. We have to go to our diagram, and we have to sum all of our forces in the y direction. So what do we have? Well, we have a normal force acting upwards, so it's positive. We have a weight acting downwards, so it's negative. So this is a 10 kilograms times 9.8 meters per second squared. 10 times 9.8 is going to be a negative 98 newtons. So we have a negative 98 newtons because it's acting downward. And then we have the vertical component of our tension. So we have plus a T sine of 30 degrees is equal to 0. Okay, so now we can see that we have two equations and two unknowns that we can solve. We have two equations and two unknowns that we can solve. So we can then solve these equations for our unknown tension T. Okay, I'm just going to rearrange these equations. And once again, we were given our coefficient of static friction, so we know what this is. Our coefficient of static friction was 0.8. So let's go ahead and just rewrite these two equations. We can call this equation 1. We can call this equation 2. And here we have equation 1 is going to be a negative 0.8 times normal force plus T cosine of 30 degrees is equal to 0. And our equation 2 is going to be our normal force plus T sine of 30 degrees is equal to 98. I'm just going to go ahead and move that over to the other side of the equation. Now you can solve these two system of equations any way that you choose to solve them. So you can solve them using matrices, like I think I probably showed you in class several times at this point, or we can solve them using substitution. It's really not that important. But what I notice right here right away, I know that I'm after the tension in the rope. So if I'm after the tension in the rope, I need to get rid of my normal force. So I'm going to take this first equation right here, and I'm going to divide the entire equation by 0.8. So if I divide the entire equation by 0.8, I get a negative normal force plus T cosine of 30 degrees divided by 0.8 is equal to 0. So I divided everything by 0.8, and now I take my second equation. I don't do anything with it. I keep it the same. I get a normal force plus T sine of 30 degrees is equal to 98. And now I can add these two equations together. What I'm trying to do is I'm trying to eliminate that normal force variable. So when I add these two equations together, I end up with a T, because my negative normal force plus a normal force goes to 0. Then I have a T. I'm going to go ahead and factor out my T, and I end up with a cosine of 30 degrees over 0.8 plus a sine of 30 degrees is equal to 98. So now I have everything. I know everything I need to know. This is just a bunch of numbers. I can plug this into my calculator. 5825. Tension is equal to 98. I divide both sides by that 1.5825, so I do 98 divided by second answer, and I get that my tension is equal to 61.9 newtons. Okay, so the second part of the problem is almost the exact same, but it asks us now that once we get the block moving, how much force is required to keep the block moving. So in this case, the block is now sliding, but we want to just keep it sliding. We're not trying to accelerate it to the right. We're trying to move it with a constant acceleration to the right. And if it's moving with a constant acceleration to the right, then it is still in static equilibrium. So it's the exact same free body diagram. The only thing that changes now is that our frictional force is just our coefficient of kinetic friction times our normal force. But other than that, everything is exactly the same. So we jump right in, we solve it with the exact same strategy that we solved it previously. We can say that the sum of our forces in in the x direction must be equal to 0. In the x direction, we have a negative coefficient of kinetic friction times our normal force plus a t cosine of 30 degrees is equal to 0. And then we have that the sum of our forces in the y direction is also equal to 0. We have a normal force minus a 98 newtons plus a t sine of 30 degrees is equal to 0. These are the exact two equations that we had before, but whereas in the previous time that we solved it, this was a 0.8. The only thing that changes now is that our coefficient of kinetic friction is simply a negative 0.6. Negative 0.6. So we're in the same sort of scenario where we have this system of equations. We have two equations, we have two unknowns. Last time we solved for tension using elimination. I just want to go ahead and work this a different way just so that everyone recognizes that there's a lot of different algebraic techniques that you can go ahead and use to solve for these tensions. And I'm going to go ahead and solve this system of equations using linear algebra. So we're going to use linear algebra. So let's go ahead and rewrite these equations a little bit in the same sort of order. So this equation, I'm just going to stay the same. This equation, I'm just going to write right above it. This is going to be n plus t sine of 30 degrees. And once again, I'm going to move this 98 over to the other side of the equation is equal to 98. Now, remember from probably your last section in algebra, we're trying to solve a 2 by 2, so two systems or two equations with two unknowns. We can do what we call is find the reduced row echelon form of the coefficient matrix, or of the augmented matrix, right? So remember that the augmented matrix is going to be the coefficients of your variables, but they all have to be in the same order. So I'm going to have my normal force variable, I'm going to have my tension variable, and I'm going to have some numerical answer that's going to be on the other side of my equation. So this is going to be a 1, a sine of 30 degrees, a 98. This is going to be a negative 0.6, a cosine of 30 degrees, and a 0. Once we have our augmented matrix, we can plug this into our calculator and we can use the reduced row echelon form function in our calculator, and it will automatically solve the system of equations for us. It'll give us both tension and normal force. So we go to second matrix. I want to go over here and I want to edit, and I already have a 2 by 3 matrix down here to edit. So that is good. Our matrix was a 1, a sine of 30 degrees, a 98. We have a negative 0.6. We have a cosine of 30 degrees, and we have a 0. Okay, we go to second quit, we go to second matrix, we go over here to math, we scroll down till we find that reduced row echelon form function, and then we plug in our matrix that we just edited. So we can see that our normal force was given to us because it goes in the same order that we had. So we had normal force as our first column. So our normal force is 72.8 newtons. And our tension in our rope is going to be 50.4 newtons. So I can do that exact same thing, or I can solve it using this method right here, and using this method right here, we found that our tension was going to be 50.4 newtons. So now we have solved this problem. We said that in order to get the block to initially start moving, it's going to require about 62 newtons. We had 61.9. In order to keep the block moving, it requires 50.4. So it goes from about 62 down to about 50 newtons. So we have a pretty big drop here in the amount of force required in order just to keep that block sliding along the ground. Okay, let's go ahead and work another friction example. This one reads, a steel block rests on a wooden incline. what incline angle causes the block to start sliding. So here's kind of what we have. So we have a steel block sitting on a wooden incline, and this incline, you can think of it almost like a board. Maybe it's initially flat and you have the block sitting on it, and as you start to increase the angle of that board, at some point you get steep enough that that block starts to slide down the slope. So, and it's asking us for what angle does that happen, okay? So this is a static friction problem, right? This is very similar to the previous problem that we just worked in, which we had a block which is initially at rest, and we are doing something that we are increasing either a force or the angle of the incline, but we're doing something to the point where that block that was stationary just starts to slide. So that means we have to overcome static friction again. So once again, we're going to overcome static friction. So whenever we have a problem like this, the first thing we're always going to do is we are going to start by drawing a free body diagram. So let's go ahead and draw ourselves a free body diagram. I have my mass sitting at some angle. It's sitting on a slope. The normal force is going to be perpendicular to that slope. So acting on this block, I have a normal force from where it contacts the incline. I'm going to have the weight of the block. Acting downwards. And then I'm going to have, when I increase this slope to the point where this block starts to slide this way, friction is always going to oppose that relative motion. So I'm going to have some force of friction acting in this direction, opposing that direction of motion, right? Opposing that direction of motion. So one of the tricks, anytime that we're solving problems that involve inclined planes, it's almost always, I'm not going to say always, but it's almost always useful to define our coordinate system such that it aligns with the incline. So I'm going to define my x-axis as being positive up the incline and my y-axis as being positive upwards away from the incline. So it's almost always simplifies the problem to rotate your coordinate system such that it aligns with the inclined plane, right? So if I go over here, I have my same coordinate systems for my block, or for my free body diagram. So that's going to be my x, that's going to be my y. And we can start looking at the forces that we have acting on this block. So we have our normal force, which is along the y direction, so it already lines up with a specific direction. And we have our frictional force, which is going to be up the incline of the slope, so it already aligns with the x direction. But our weight now is in both the x and the y direction. So we have to split this up into its components. When we split this up into its components, we get that we have a component of the weight that acts in the y direction and a component of the weight that acts down the incline. If our incline is at an angle theta, that same angle theta is right here. You can do the trig and prove it to yourself if you don't believe me, but that is going to be your angle of your weight when you split your weight into its x and y components. So this is going to be my weight in the y direction, and this is going to be my weight in the x direction. Okay, well, once we get to this point, this becomes a pretty straightforward problem to solve. Once again, it's a static equilibrium problem. We are looking at the instance right before the block starts to slide. So right before the block starts to slide, it still has an acceleration of 0, which means that we can say that the sum of our forces in the x direction are equal to 0, and the sum of our forces in the y direction are equal to 0. So let's go ahead and do that. We can say that in this case, I'm going to go ahead and I'm going to start with my y direction, and you'll see that here in a second, or why we're doing that here in a second. But we're going to say that the sum of our forces in the y direction is equal to 0. What do we have acting in the y direction? Well, we have a normal force acting upwards, so it's acting in the positive y direction, and we have a component of the weight acting downward in the negative y direction, so we have a negative weight cosine of theta is equal to 0. Negative weight cosine of theta is equal to 0. Okay, I want to go ahead and simplify this a little bit more. I should have maybe done this when I did my free body diagram. Recall that the weight of the block is going to be equal to the mass of the block times gravity. I'm going to go ahead and plug that into my equation here. So this is going to be an mg cosine of theta degrees is equal to 0. Okay, our second equilibrium equation is going to be that the sum of our forces in the x direction must be equal to 0, and acting in the x direction we have a frictional force. And just like last time, because we have impending motion, or we're taking this block right up to the point where it's about to slide, we know what this is. This is going to be equal to the coefficient of static friction times our normal force. Or sorry, our coefficient of static friction times our normal force. So we know what our frictional force is going to be. So what do we then have acting in the x direction? Well, we have friction. It's acting in the positive x direction. So we have our coefficient of static friction times our normal force. And then we have the component of our weight in the x direction acting down the slope in the negative direction. So we have a minus mg sine of theta is equal to 0. So now I have two equations that I'm trying to solve for. I'm really interested specifically in theta. I'm interested in theta, but once again, just like last time, we don't know what our normal force is. We know what the mass of the block wasn't given. We're going to see that it doesn't matter here in a second, but we know what g is. It's 9.8 meters per second squared. Theta is what the problem is after. The coefficient of static friction, we have it written numerically here, and I'm going to keep it that way, but recall that they gave us in the problem that it was a steel block on a wooden incline. So we can go to our table and we can look up what the coefficient of static friction between steel and wood is, so we actually know what this value is. Once again, we don't know what normal force is, and we don't know what theta is. So we need to be able to work these problems. Let's try and work this problem or combine these two equations together and see if we can solve for theta. Let's see if we can solve for theta. So how I'm going to solve these two system of equations is I'm going to use the substitution method. What I'm going to do is I'm going to solve the sum of our forces in the y direction for our normal force. And once we have our normal force in terms of our other variables, we will plug that into our x equation. So this equation becomes that our normal force is equal to mg cosine of theta. I can take this and I'm going to plug it into our x equilibrium equation. So now I have that my coefficient of static friction times mg cosine of theta minus mg sine of theta is equal to 0. I can go ahead and move this negative value over to the other side of my equation. So I get that my coefficient of static friction, mg cosine of theta is equal to mg sine of theta. I have an mg on both sides of my equation, so as it turns out, the mass of the block and the acceleration due to gravity don't matter. The mass of the block and the acceleration due to gravity don't matter. That's a really interesting takeaway. Let's go ahead and solve this problem all the way. I can divide both sides by cosine of theta, so I get that my coefficient of static friction is equal to sine of theta over cosine of theta, which is just equal to the tangent of theta, Now we go and we look up in a table, and we said that the coefficient of static friction between steel and wood ends up being 0.5. 0.5 is equal to the tangent of theta. And if I want to determine theta was what the problem was asking for, I take the tan inverse of both sides, and I get that theta is equal to the tan inverse of 0.5, which means that theta is equal to 26.6 degrees. 26.6 degrees. So if I have this block on an incline and I increase that incline to 26.6 degrees, that is the point in which that block will start sliding down the incline. Okay, then, like I said, I want to talk about what happened. Let's really quick briefly touch on what just happened here. A couple interesting things. First of all, mass doesn't matter. It doesn't matter if it's a 1 kilogram block, if it's a 2,000 pound block, if it's a 10-ton block. It doesn't matter. Any block, wooden block on a steel block on a wooden surface, when it hits that 26.6 degrees, is always going to slide. The mass doesn't matter. It only ends up becoming a function of the coefficient of static friction, which only depends on the two materials, not on the mass of those materials, just depends on what those two materials are. The other interesting takeaway is that G cancels out. The acceleration due to gravity cancels out. So that means if I was to have a steel block on a wooden incline on the moon or on Mars, it doesn't matter. Any gravitational acceleration, it will still start to slide at that same 26.6 degrees. Let's talk about a special application of static friction, and we're talking about with respect to a rolling wheel. So when we have a wheel that is rolling along a surface, such as this wheel right here, assume this direction of rotation is kind of indicated in the photograph, even though the wheel is in motion, this contact point right here, this contact point is not slipping. It is not moving with respect to the ground. So even though the entire center of the mass of the wheel is moving to the right, this exact contact point where this wheel contacts the ground is not moving. So unless we're doing something like a burnout in a car where your tires are actually slipping along the surface, as that wheel rotates, typically you're going to assume that your contact point has zero relative velocity with respect to the ground. With that being the case, we would use our coefficient of static friction when we talk about a rolling wheel, and this becomes very important when we talk about things like braking in cars. Okay, let's go ahead and work another one. So this question asks, what is a rear-wheel drive car's maximum acceleration on flat pavement if it has a 50-50 weight balance? Okay, what is the maximum acceleration of a rear-wheel drive car? So let's go ahead and real quick throw up a free body diagram. So I have my car, so it doesn't really matter, I'm not much of an artist. We have our car, it has two contact points. It has two contact points if we are going to simplify this to a two-dimensional problem, which we are. So what we are assuming is we are assuming that the left tire and the right tire carry the same load. So the front left tire, the front right tire carry the same load, and the back left tire and the back right tire carry the same load. So what do we have then acting on this car? Well, we have the contact force, the normal force from the rear tires, and we have the contact force from the front tires, and we have the weight of the car acting in the y direction. So I can say that I can call this, it doesn't really matter, let's call it normal force 1 and normal force 2. Okay, the next big assumption that the problem says is that if we have a 50-50 weight balance, what that means is a 50-50 weight balance in a car means that your center of mass is directly in between your wheels, which means that these both carry the same load. These both carry the same load, and so what that means is our normal force 1 is the same as our normal force 2. So I'm just going to go ahead and simplify this into the same normal force. So we have a normal force acting here and a normal force acting here. Okay, now if this is the windshield of the car, which means that it's going to move this way, I don't want to draw that arrow, don't make you think that's a force. If it's going to move that way is going to be positive forward in the x direction. A car, when it's being driven by its rear tires, that drive force is coming by the frictional contact between the rear tires and the pavement, right? The frictional contact by the rear tires and the pavement. As we try and rotate these rear tires, it propels the car forward, so we have a frictional force. We have a frictional force acting here. We have a frictional force acting here. Now, we just talked about for a rolling tire, if we do not have relative motion between the tire and the pavement, that this is going to be dictated by the coefficient of static friction, because a rolling wheel is not sliding. There is no relative motion between the wheel and the ground. That means that we know that our frictional force here is going to be our coefficient of static friction times our normal force. Our coefficient of static friction times our normal force. So we just about have everything that we need to know in order to solve this problem. The last piece of information that we're kind of missing is we're saying, okay, if it's a rubber and concrete, so rubber tire meeting a concrete road, we go and we look it up in our table, and our coefficient of static friction between rubber and concrete is 1.0. 1.0. Okay, now we can say if we want to go ahead and solve this problem, we're after the maximum acceleration. The acceleration is going to be in the x direction, but we're going to go ahead and we're going to go back to Newton's second law to solve this problem. So Newton's second law is going to be that the sum of our forces is equal to our mass times our acceleration. This is a vector equation. This is a vector equation, so we can split this up into components. So our first equation I'm going to look at is I'm going to specifically look at the y direction. So if this is the positive x direction and this is the positive y direction, I can say that the sum of our forces in the y direction must be equal to 0, because if we were to have acceleration in the y direction, that would mean that the car is going to take off into the air, which we know doesn't happen, or it's going to bury down through the dirt, which we also know doesn't happen. The car is going to just travel along the pavement, so our acceleration in the y direction must be equal to 0. So that becomes that our sum of our forces in the y direction is we have 2 normal forces, both acting upward. So we have 2 times our normal forces, both acting upward, minus our weight, which is going to be our mass times our gravity, is equal to 0. So the weight of the car is going to be equal to the mass of the car times our acceleration due to gravity. So this becomes 2 times normal forces, because we have 1 normal force at the rear tires and we have 1 normal force at the front tires. Okay, our next equation that we have is we have that our sum of our forces in the x direction is going to be equal to our mass times our acceleration in the x direction. This is very important. This car, we're asking what the car is going to accelerate in the x direction, so this value is not 0. This value is not 0. Okay, so what do we have acting in the x direction? So acting in the x direction, we only have one force. We only have the frictional force acting at the rear tires. So we say that the sum of our forces is going to be coefficient of static friction times our normal force is going to be equal to our mass times our acceleration in the x direction. I have this coefficient of static friction times this normal force is equal to the mass times the acceleration, and the problem is after the value of this acceleration. I can't solve this equation right here because I have too many unknowns. The mass of the car wasn't given. I don't know what the normal force is. I know what this is. This is 1.0. We looked it up in a table, but I'm after acceleration and I don't know what these two values are. So I must have to go back to our other equation and see if I can solve it such a way that it simplifies this problem. And in fact, it does. I can move this mass times gravity over to the other side of the equation and then divide both sides by 2. And I get that my normal force is equal to mg over 2, which makes sense, right? We're saying the car has a 50-50 weight balance, so that means that each tire is supporting half of the weight. Each tire supporting half the weight. So this becomes, I'm going to start plugging in my known values. I know what my coefficient of static friction is. It is 1.0. We just found that normal force is going to be mg over 2. It's going to be equal to our mass times our acceleration in the x direction. And now we see that the mass of the car is no longer important because mass is on both sides of the equation, so it cancels out. So I get that my acceleration, and this is just a multiplication times 1, so that gets that my acceleration in the x direction is just going to be g over 2, which is just 9.8 over 2, which is just going to be 4 points, whatever it is. 4.9 meters per second squared. So with the problem that it feels like they gave us minimal information, right? The problem feels like they gave us minimal information. They just said that we have rubber tires on a concrete pavement. They said that our weight balance was 50-50, but they didn't give us what the mass of the car was. They didn't give us any other information other than that. With something that seems like minimal information, we are still able to figure out what the maximum acceleration due to the 50-50 weight balance and due to that rubber contacting the concrete would be for this car. In that case, it's going to be 9.8 meters per second squared, or half a g. So half a g. So a typical car can accelerate at about half a g would be the maximum acceleration that you could get from kind of a standard rubber tire. So let's do some analysis about that then. Let's do some analysis about that problem, and let's think about if I wanted to have a faster acceleration than that, if I wanted to have a faster acceleration than that, like a drag race car, for instance, how could I increase this acceleration? How can I increase acceleration? Well, there's two different things that we can do. The most obvious one is we can figure out some coefficient of static friction that's higher than 1, and that may not make a lot of sense that you think about something being tacky or something being sticky. If you have a sticky surface contact, you can in fact have coefficients of static friction greater than 1. In fact, your kind of rubber stickum that they use on professional drag race cars has a coefficient of static friction of almost 4. So you can have much higher coefficient of static friction than 1. So having stickier tires, something that stick to the ground and have a greater coefficient of friction, will increase your maximum acceleration. The other way that you can increase your maximum acceleration is you can move your center of gravity of your vehicle back over your drive tires. So if you have a rear-wheel drive car, if you go from a front engine car to a mid-engine car, you're moving your center of gravity from the front towards the back, so you're increasing your weight over your rear tires, and you're going to increase your acceleration because these are no longer equal anymore. Now you're going to say, okay, I may have 2/3 of my weight over my rear tires and 1/3 of my weight over my front tires, and that's going to give me more frictional force that I can use to propel my car forward. So we can say, based off of this problem, we've already identified some ways that we could make a car accelerate faster if we were able to do so. So let's work another car example, because I like car examples. You deal with cars every day of your life, so you're familiar with them. So I like trying to work examples with things that you know and kind of pertain to your day-to-day life. So let's work an example where we have a car, a 3,000-pound car is traveling. So here's my car. It's 3,000 pounds, and it's traveling. It was given at 88 feet per second, as the problem states. Okay, now it's on a level road, and the driver slams on his brakes, and he causes the brakes to lock up. And what that means is that the wheels just stop turning, and he starts to skid down the road. So all of a sudden, he starts to skid down the road. Here are my skid marks left by the car until he finally comes to a stop. At some distance later. So I'm asking you, how far does this car travel when those wheels are locked up until it comes to a stop? So this is, in fact, a friction problem again, but we are going to go ahead and combine this with our 1D kinematics that we learned in Chapter 2. So, in order to solve this problem, what we are going to do is we're going to make the assumption this car kind of behaves like a point mass, or a point mass. So we can assume all the forces acting on it pass through its center of mass, and we can say, okay, it doesn't really matter that I only have 2 contact points between my front and my rear tires, because the total of the normal force, N1 and N2, is always going to be equal to the weight of my car. So it's always going to be equal to my 3,000 pounds. So let's just go ahead, you know what, let's not make the assumption. I think this will make a little bit more sense if we go ahead and work out that problem, or work it out right here. So let's draw ourselves a free body diagram of what we have acting when we have the brakes locked up and we're skidding along the side of the road. Here's my car, and it weighs 3,000 pounds. So we know right off the get-go that we have a 3,000 pounds of weight acting downward on my car. Okay, we have a contact point with the rear tires and the front tires. So we have a normal force, we'll call it normal force rear, and normal force front. We don't know what the values of those cars are. Okay, now when the brakes have locked up, we are assuming, or we're saying, that all 4 tires are locked up. So both the rear tires and the front tires are locked up. So we are going to have a frictional force acting from both the rear and the front tires. We're going to have a frictional force acting from both the rear and the front tires. So I can call this my frictional force acting at the rear and my frictional force acting at the front. Okay, and this is all of the forces that we have acting on this particular vehicle, right? All the forces that we have acting on this particular vehicle. So we can go ahead and we can jump into the same sort of problem that we worked last time and apply our equations of motion from Newton's second law. Once again, we can start with our y direction, and we can say that the sum of our forces in the y direction must be equal to 0, because if we define our coordinate system as the standard x to the right, y up, if we had acceleration in the y direction, the car would take off into the air or it would accelerate down through the ground, which we know doesn't happen. So the sum of our forces in the y direction must be equal to 0. So we can then say that our normal force rear plus our normal force front minus 3,000 pounds is equal to 0, or we can just move that 3,000 pounds over to the other side of the equation, which just means that if we sum up our normal forces, they should sum to be 3,000 pounds, which is the weight of the car. So we're all good there. That totally makes sense. Okay? Now, our next equation that we're going to do is we're going to solve our sum of our forces in the x direction, and that's going to be equal to some mass times some acceleration in the x direction, because we are slowing down. This car is slowing down as it skids across the ground, which means it has an acceleration pointing that way. If it initially has a velocity to the right and it's skidding and it's slowing down, then its acceleration is back to the left. Its acceleration is back to the left, which means the acceleration is going to have a negative value. It's going to have a negative value. So let's go ahead and solve for that right here. So what do we have acting in the x direction? Well, we have our frictional forces. We have our frictional forces, and because the car is skidding, where the rubber and the concrete pavement are meeting, there is relative motion. There is relative motion, so that means that this is going to be equal to the coefficient of kinetic friction times our normal force in the rear. That's going to be our rear frictional force. And our front frictional force is going to be our coefficient of kinetic friction times our normal force from the front. Okay? Don't get confused by the arrows. We'll do equal signs so that we know what those values are. So we can say that we have a negative coefficient of kinetic friction because it's acting to the left times our normal force from the rear minus our coefficient of kinetic friction from our normal force to the front. It's going to be equal to our mass times our acceleration in the x direction. Equal to our mass times our acceleration in the x direction. Okay, both the rear and the front tires are both made of rubber. They're both made of rubber, and the ground is still always going to be the concrete from the road, so the coefficient of kinetic friction is going to be the same. So if I go ahead and factor out this coefficient of kinetic friction, I end up with a normal force from the rear plus a normal force from the front. It's going to be equal to our mass times our acceleration in the x direction. And here we can say that our normal force from the rear and our normal force from the front is the same as what we solved for in our summation of our forces in the y direction. So I want to go ahead and step back to this equation for a second. I probably should have done this from the beginning, and it would have made it less confusing. As it turns out, when we solve this problem, the fact that the car weighs 3,000 pounds doesn't matter. The fact that the car weighs 3,000 pounds doesn't matter. In fact, really all that we care about is that it is the weight of the car acting downward, which we know is equal to our mass times our acceleration due to gravity. So I'm actually going to rewrite this. Instead of doing it in terms of actual numbers, I want to solve it symbolically. I'm going to solve it in terms of variables here so that we can see what sort of things cancel out. So as it turns out, this is going to be our normal force from the rear, our normal force from the front, which are acting upwards, are equal to what we have acting downwards, which is going to be our mass times our gravity. And hopefully now this makes a little bit more sense, because I know what my normal force from the rear and our normal force from the plus our normal force from the front is. It's just our mass times our gravity. So this becomes a negative coefficient of kinetic friction times our mass times our gravity is equal to our mass times our acceleration in the x direction. In this case, our masses cancel out. So the fact that this car, once again, remember 3,000 pounds is going to be the weight of the vehicle. If I wanted its mass, I divide it by 32.2 to get its mass in slugs. But it doesn't matter what the mass of the car is. As we do our problems, our masses ended up canceling out. So we end up getting that our acceleration in the x direction is equal to negative our coefficient of kinetic friction times our acceleration due to gravity, which we know what these values are, or we can go look it up. We can say that for a dry rubber on concrete, the coefficient of kinetic friction is 0.7. We are in American units, so this needs to be in 32.2 feet per second squared. So this becomes a negative 25 or 22.5 feet per second squared. This is going to be the acceleration of our car in the x direction. The acceleration of our car is negative 22.5 feet per second squared. Okay, so let's make a note of that up here. We said that our acceleration in the x direction is negative 22.5 feet per second squared. Okay, so now that we solved all that, we solved that problem in order to determine what our acceleration is due to braking. This just becomes a kinematic problem. This becomes a one-dimensional kinematic problem, and they're asking for the distance that this travels. The distance that this traveled. So they're not asking for the time. They give us an initial velocity. We know the final velocity is going to be 0. It's asking the distance that it travels until it comes to rest, and they're asking for some delta x. So we are going to use our distance velocity relation equation, which we say that our final velocity squared is equal to our initial velocity squared plus 2 times a times delta x. Remember that from our one-dimensional kinematic equations? So we know that our final velocity is 0 because we're coming to a rest. So we have 0 squared is equal to our initial velocity was 88 feet per second squared plus 2. Our acceleration we found to be negative 22.5 feet per second squared times delta x. So now we know everything in this equation. As it turns out, we have delta x is going to be 88 squared divided by 2 times 22.5. I just moved this negative value to the other side of the equation. I divided both sides by 2 times 22.5. It gives me delta x. And as it turns out, this is 171.8 feet. 171.8 feet. So this 88 feet per second is the same as about 60 miles an hour. So I gave that to you in your class notes, but if you're traveling at 60 miles an hour, and you slam on your brakes and your brakes lock up, it's going to take you 172 feet to skid to a stop. It's going to take you 172 feet to skid to a stop. This is why it's so important to make sure that you have a good follow distance with the car in front of you when you're driving on the highway. The other big takeaway from this is recall that the brakes are locked up. And when the brakes are locked up, we used our coefficient of kinetic friction, which is 0.7 for rubber and concrete. Most modern day cars have anti-lock brakes. You know, if you ever slammed on your brakes super hard and you hear the pedal it bounces, it vibrates against you, that's an automatic device, a safety device built into your brakes that it senses when your wheel speed stops, and when it recognizes that, it pulses your brake in order to try and unlock up your brakes. Now, we said that for a rolling wheel, if there is no slipping between the wheel and the ground, we use our coefficient of static friction. So in that case, if you can make sure that your wheels don't lock up, you can use your coefficient of static friction, which for rubber and concrete goes from 0.7, which is kinetic, it goes to 1.0 for static, and that would decrease your distance that it would take to stop to about 120 feet. So you cut over 50 foot of stopping distance off your braking distance if your wheels don't lock up. So that's the importance of why anti-lock brakes have been kind of adopted by all modern cars, is those anti-lock brakes are what keep your wheels from locking up. And if you can keep your wheels from locking up, you get to use that coefficient of static friction between the rubber and the ground, and it can greatly decrease the distance that it requires for you to brake to a stop. Okay, so now that we've talked about friction, let's talk about another kind of a specific type of friction, which we call drag. So drag is I guess the friction that we talked about previously is friction between two solid surfaces. So if I have two solid surfaces in contact and I have a relative motion between those two surfaces, we call that friction. Where drag is kind of a specific type of friction that occurs between a solid surface and a surrounding fluid. So we have two kind of main types of drag that we're going to talk about. The first one is going to be air resistance, which I'm going to come back to here in a second, and the other one is going to be hull drag. So hull drag, of course, is a boat. As a boat travels through the water, all that contact area between the hull of the boat and that water, there exerts a drag force as that boat tries to move through the water. The one that we're going to focus on for this section is we're mostly going to be talking about air resistance. And air resistance is the same sort of thing, but it's the drag that happens when you have a solid body that moves through the air. So for example, we have an airplane here, a free body diagram of an airplane. So we have the thrust acting from the engines acting in the positive x direction, if I define the positive x direction to be to the left here, and we have drag acting to the right, so opposing that relative motion. Of course, we have lift from the wings that lift the airplane, counteracting the weight, but what we're specifically after is the drag. Now, drag is a very well-studied phenomena in physics, especially in engineering, because if I can reduce the drag on things like airplanes or cars as they move through the atmosphere, I can improve the economy, the fuel economy of these vehicles, and reduce the amount of fuel that I'm burning. That's better for the environment. That saves everybody money from having to pay for fuel. So this is an example of why drag is so important. Now I want to make sure this last kind of bullet point here, what I want to make sure is very clear is that drag happens anytime that you have a relative velocity with a solid body moving through a fluid. That doesn't mean that the fluid is always stationary and the body is always moving. You can also have a stationary body in which the fluid moves over it or moves around it. So for example, if I'm standing still on a windy Amarillo day and I experience that force as that wind tries to blow me over, that is still a type of drag. That is that there is relative velocity between me and the wind because the wind is moving, even if I am not. And that will exert a drag force on me as well. So drag, remember when we talked about friction, we had that model, that extremely rough surface. We had that, that rough surface and how they interact, and we said that the way that those surfaces interact is actually very, very complex. And we kind of lumped all of that complexity into some constants, the coefficient of friction, that we develop empirically. So we can take something that's incredibly complex, we can do a bunch of experiments, and then we can simplify that complexity into a relatively simple mathematical expression, and that kind of slush constant, the coefficient of friction, is how we can make something complex incredibly simple. Well, we've done the same sort of thing with drag. It's just a little bit more complex than normal friction, right? So it's a little bit more complex than normal friction. So we have what we call what we have here is the model that we use to approximate the force that drag has, the force of drag on a solid body. Okay, so we have a 1/2 c rho av squared. We have let's kind of define what these constants are. C is something that we're going to call the drag coefficient. Drag coefficient, just like coefficient of friction, it is also unitless, but it is a coefficient that depends on the shape of the solid body that is moving through the fluid. Okay, and the next one is rho. Rho is going to be the density of the fluid that we're moving through, or is moving with respect to the solid body. A is going to be the frontal area of the body, and then V is going to be the velocity. So we're going to talk about all of these in a lot more detail here in a second, but I want you to know a couple things here is that we are directly related to the coefficient of friction, the density in the frontal area, but we are related, or we are proportional to the velocity squared. So the velocity squared is proportional to the force of the drag. So that means as we increase the velocity, the force of the drag increases with that velocity squared. So the force actually grows parabolically with velocity, not linearly like it does with the other constants. So, like we said, the drag coefficients are dependent on the shape of the body. So we have done a lot of experiments, or scientists and engineers have done a lot of experiments over the years, and they've determined the drag coefficients for a lot of different shapes. And I kind of have some just simple shapes listed over here in this table, right? So these are all kind of defined like I say, empirically by doing experiments, and we kind of have a good idea of what these drag coefficients are from lots and lots of experiments. Now, I want you to take a note here of how wild the variation between these constants is. So, for example, the streamlined body has a drag coefficient of 0.04, so very, very small, whereas a cube on end to the direction of the flow, so this direction of this arrow is the direction of the flow of the fluid with respect to this this solid body. But if we have a cube on end where its flat face is facing the direction of flow, it has a drag coefficient of 1.05. So we can make a huge difference. We can make a huge difference in reducing the force of drag by increasing the aerodynamic shape of our body. This is why, you know, after they kind of went away with square body trucks in the 70s and 80s, how modern day cars are so much more, there's so much more emphasis on having a streamlined shape. And we're doing that to try and increase fuel economy. Whereas, like you say, those old square bodies are just have a big flat front. They have a very high drag coefficient. They get very poor fuel economy. So why would we say, how does the shape kind of affect why this drag coefficient is so different? So I have two examples here. I have a sphere and a streamlined body. You'd think, okay, well, a sphere is smooth and a streamlined body is smooth. They should have similar drag coefficients, but if you look here, they don't. In fact, there's an order of magnitude difference. The sphere's drag coefficient is more than 10 times higher than a streamlined body. Well, why does that happen? That has something to do with pressure drop as that flow goes over that body. So for instance, for a sphere, as that fluid flows around that body, it reaches a point where that flow will detach from the surface of that body. So that flow is kind of nicely following the contour of the sphere until it reaches this point. And once it reaches this point, it starts to detach from that body, and you get these turbulent eddies that form behind that sphere. Now, these turbulent eddies are going to have a low pressure. They're going to be lower pressure than everything else. So if we have a high pressure on this front side of the sphere, a low pressure on the back side of the sphere, what you end up with is you end up with a net force acting to the right. You end up with a net force acting to the right. Now, for a streamlined body, in the direction of this flow, we have this nice long tapered shape. And when you have this nice long tapered shape, what that does is that keeps that flow from detaching. It keeps that flow from forming these turbulent eddies with low pressure zone turbulent eddies behind that shape, and it greatly reduces the drag. So this is kind of an example of what engineers are looking at when they're trying to design a shape that has a low drag coefficient. So the next thing that we're going to talk about, we're just going to kind of go through the order of this equation here. So we just talked about the drag coefficients. Now we're going to talk about the fluid density. So the fluid density is going to be proportional to the drag force, meaning that if we are moving through a thick fluid like water, which is, you know, it's very dense with respect to air, you're going to have a much higher drag force in water than you are in air, which makes sense, right? So we typically are going to be working with air or water in this course. So if we're working with water, I kind of give you the density of both fresh water and seawater down here. But if we're working with air, the air density actually changes depending on temperature and pressure. So as we increase in altitude, we lose temperature, so the air gets cooler, but we also lose pressure as you increase your altitude. So your density has an effect of decreasing with altitude. So you can see at sea level, we have a air density of 1.225 kilograms per meter cubed. But if we go all the way up to 10,000 meters, which is, you know, over 30,000 feet up where airplanes fly, our density is less than half, significantly less than half, at 0.4135 kilograms per meter cubed. Our next variable that we're going to consider is what we call the frontal area. And the frontal area is specifically the area that you see if you are looking in the direction of the flow at the at the solid body. So if we have an airplane moving through the air, the frontal area is kind of shown in blue here. Not the entire surface area of the plane, just this frontal area. If we projected this airplane onto a plane that was perpendicular to the flow, we would have this kind of area. So for example here, a cylinder, if we have a cylinder and the flow is parallel to the length of that cylinder, the frontal area is just going to be a circle. Okay, so we have one last thing I want to kind of talk about here. And you say, okay, Zach, the equation was 1/2 drag coefficient rho AV squared. If I have this 1/2, why can't I just lump that 1/2 in with my drag coefficient, cut all my drag coefficients in half, and get rid of that 1/2? Well, as it turns out, we actually keep that 1/2 for a reason. There's something that we call dynamic pressure, which we're going to cover in chapter 12. And dynamic pressure is going to be rho v squared over 2, or density velocity squared over 2. So our force of our drag is actually given by our drag coefficient times the frontal area times our dynamic pressure. So I just want to make sure that's why we don't just kind of lump that drag coefficient and that 1/2 in together. We keep them separate so that we can use them in terms of our dynamic pressure, which we will cover in later chapters. Okay, let's go ahead and work a drag example. The problem reads, a Dodge Ram which has a drag coefficient of 0.43 and a frontal area of 1.21 meters squared is driving along the coast at sea level where the density of the air is 1.225 kilograms per meter cubed at a velocity of 100 kilometers per hour into a 30 kilometers per hour headwind. What is the force of drag acting on the truck? Okay, so we're just going to jump right into our force of drag equation, which we just said is 1/2 drag coefficient, fluid density, frontal area, velocity squared. And they gave us everything in the problem that we need to solve but velocity. So they gave us our drag coefficient, they gave us our frontal area, and they gave us the density of the fluid that we're moving through. So what we're missing here is we are just missing the velocity of the truck. Now this is just one little kind of caveat that we have here. If the truck is moving at 100 kilometers per hour, but it's moving into a 30 kilometer per hour headwind, then the relative velocity of the truck with respect to the fluid is 130 kilometers per hour. And that should make sense. We're not necessarily interested in the velocity of the truck with respect to the ground. We're interested with the velocity of the truck as it moves through the fluid. So in this case, because the truck and the fluid are both moving and they're moving in opposite directions, the total relative velocity between the two is going to be them summed together. So that means that we can say that the velocity of the truck is going to be equal, or with respect to the air, is going to be equal to 130 kilometers per hour. All of our other units are going to be in meters and are in meters, and we know what our hours is kind of not our standard units. So what we need to do is we need to then convert this value back into our standard meters per second. So that's pretty straightforward. We should be getting really good at this now. I want to get rid of kilometers, so I put 1 kilometer on the bottom of my fraction, 1,000 meters on the top of my fraction. I want to get rid of hours, so I have 1 hour on the top of my fraction, and there are 3,600 seconds in an hour, and that goes on the bottom of my fraction. So my kilometers cancel out, and my hours cancel out, and I'm left with meters per second. So if I plug all that into my calculator, I end up getting that my velocity is 36.11 meters per second. So now I have everything I need to just plug into my drag force equation. So let's go ahead and do that. So my force of drag is going to be equal to 1/2. My drag coefficient was given to be 0.43. The density of the air is 1.225 kilograms per meter cubed. My frontal area is 1.21 meters squared. and my velocity was 36.11 meters per second, and I square that entire term. So I have everything in standard units. I know all these numbers. These are just numbers. I plug them into my calculator, and I get that my force of drag is 416 newtons. So let's consider the specific case in which we have a solid object falling through air. It doesn't have to be air, it can actually be any fluid. So let's just say a solid object falling through a fluid. Well, as we said, the force of drag increases parabolically, or increases with the velocity squared. So if the object is initially at rest, the force of drag is 0. So what we have acting on it is we have gravity, and gravity will cause that object to accelerate downward. As that object accelerates downward, its velocity will increase and increase and increase to the point where the force of drag will eventually equal the weight of the object. And at this point, we call that the terminal velocity, because what we have is we have an object that is in equilibrium. That means that the force of drag acting upwards is going to be equal to the weight acting downwards. So if we have a force, no net force acting on this object, because we have a force acting up which cancels out a force acting down, meaning we have 0 net force acting on this object, then it will continue to fall with 0 acceleration. If the acceleration is 0, then it falls at a constant velocity, which we call the terminal velocity. So let's go ahead and work a terminal velocity example problem here. And I just want to go ahead and quick show you kind of where this equation that we gave you in the notes comes from. So if I have a mass that is falling through the air, we define what we call terminal velocity is the point in which the mass stops changing in velocity. So if it starts from rest, it accelerates to some terminal velocity, and then it continues to just fall at that constant velocity the entire time. So we can say that that happens when our weight of our body, which is going to be our mass times our gravity, is going to be equal to our drag force, which is 1/2 coefficient of drag rho a v squared. If we're falling at a constant velocity, that means acceleration is equal to 0. If acceleration is equal to 0, then the sum of our forces in the y direction must be equal to 0. So I get that the forces acting upward is 1/2 c rho a v squared minus mg is going to be equal to 0. Now I can solve this equation for my terminal velocity. That's all I do is I just take this equation and I'm solving it for my terminal velocity. So I'm going to move my mg to the other side and I'm going to go ahead and multiply it by 2. So I get that as c rho a v squared is going to be equal to 2mg. I divide both sides by c rho a. V squared is going to be equal to 2mg divided by c rho a. I take the square root of both sides and I get my terminal velocity equation. So now that we know what our terminal velocity equation is, we can just plug values into it. So let's go ahead and do that. Our problem reads, a 55-kilogram skydiver jumps from a helicopter and achieves terminal velocity after traveling some distance. Calculate the terminal velocity of a skydiver if the density of the air is 1.21 kilograms per meter cubed, the cross-sectional area of the skydiver is 0.6 meters squared, and the drag coefficient is 0.7. Okay, so this becomes a really, really simple equation to solve because the problem gave us everything that we need to know to solve this problem. So this becomes the square root of 2. The mass of the skydiver was given to be 55 kilograms. Gravitational acceleration is 9.8 meters per second squared. We have the drag coefficient was given for the skydiver to be 0.7. The density of the air was given to be 1.21 kilograms per meter cubed. And his frontal area was given to be 0.6 meters squared. So now it's just as simple as plugging all this into your calculator and solving it. And when we plug it into our calculator, we get that the terminal velocity is going to be 46.1 meters per second. Now, if we wanted to convert that to some units that maybe we're a little bit more familiar with, this is the same as saying that his terminal velocity is 166 kilometers per hour, which is the same as 103 miles per hour. And this is order of magnitude correct. So when you're skydiving and you jump out of a plane, obviously you can change your terminal velocity quite a bit by controlling your body shape. So imagine if I'm falling towards you right now, if I spread myself out wide, I really increase my frontal area and I increase my drag coefficient. But when they pencil and they have their helmet going straight down towards the ground, they greatly reduce their frontal area and they greatly reduce the drag coefficient. So there's a lot of variability in your terminal velocity for skydiving, but order of magnitude, this is about right. You fall at somewhere around 100 miles per hour when you are skydiving. Okay, section 5.3 in the textbook deals with elasticity and stress and strain, which I think are a little bit beyond the scope of kind of a college physics 1 type course. This is more engineering based, and I don't really want to get into it. But what I want to do instead is I want to talk about kind of a simpler model of spring. So as it turns out, everything in the world can be approximated or behave similarly to very stiff springs. So when you get down to it, elasticity, stress, and strain is actually the same material as for springs, but we're just going to look at it as kind of a more simplified model, and we're going to specifically look at springs themselves. So what we're going to do, let me go ahead and hide this. What we're going to do is we're going to talk about spring. So a spring is an object that can be deformed by a force and then returned to its original shape. And we all kind of understand that. Everyone's seen a spring. You can push on a spring and it compresses, or you can pull on a spring and it can elongate. But when you take that force that you applied off that spring, it returns back to its original length. So a lot of times you're going to hear that original length be called its natural length, its free length, or its unloaded length. If I use any of those terms, those are all going to mean the same sort of thing. So how much that spring either compresses or elongates is actually given by what we call Hooke's law. So Hooke's law is given as the force of a spring is equal to negative K times L minus L sub n. What do those constants mean? So F is going to mean the force exerted by the spring. The force being exerted by the spring is going to be equal to negative the spring constant, and this is going to be dependent on the spring itself. So we're almost always going to be either given the spring constant, we may have to solve for the spring constant, but the spring constant is going to be determined by what material is the spring made of, how thick is the wire that is used to make the spring, the heat treatment that has to go into the spring. So there's a lot of things that go into the spring to determine its K value, but that'll be a property of the spring itself. And then finally, we have L minus L sub n. What L is going to be, L is the deformed length. So this may be shorter or longer than the natural length, depending on compression or elongation. And then we have L sub n, which we're going to talk about, is the natural length. A lot of times, you'll classically see Hooke's law given as the force is equal to negative Kx. And when we have this x is defined as that same displacement. So if we have this same picture that we had before, this picture shows that what we started out with as some undeformed length, some undeformed natural length, and then we apply a force to that spring and it grows to some final length L. Well, that change in length is going to be what we call x. Now, I want to talk about this negative sign. So it's really easy to get confused with this negative sign, and this negative sign is kind of classically given in Hooke's law. All that negative sign indicates is that the force that the spring exerts is going to be in the opposite direction of the change in length. So for instance, we have an externally applied force here to the right that is causing this spring to elongate. If we define the positive x direction to be positive to the right, all that negative means is that spring exerts an equal and opposite force to the left, which is going to be in the negative x direction because it opposes the change in elongation. So don't get too bent out of shape about this negative sign. It's really easy to get confused about this negative sign. What I prefer to do is when we have our Hooke's law, I usually just look at the magnitude. So the magnitude of the spring force is just going to be equal to the magnitude of kx, which we can get rid of that negative sign, and then we will analytically look at the problem and we will determine what direction the force is based off of what the question is asking for. So sometimes we may be given a problem in which we do not know the natural length of the spring. So for instance here, this is what I want to make sure that everyone kind of understands. If we look at this second form of Hooke's law, the force that the spring applies is going to be linear with respect to that change in length, or with respect to that free end displacement. And because it's linear, a lot of times we can think of it in terms of a change in force is going to cause a change in elongation. So a change in force is going to be equal to a change in elongation, and this is a really helpful form of this equation, like I said, when we do not know the natural length of the spring, and I'm about to work a problem that we show how we can use that here in a second. So there's a couple things that we have to assume, or there's a couple requirements that we have to have be true in order to use Hooke's law for a spring. And the big one is Hooke's law is only valid for when the spring is elastically deformed. So elastic deformation occurs when you can stretch or compress that spring and then it returns back to its original dimension. This is called a reversible non-permanent deformation. We call that elastic deformation. But as anyone who's ever worked with a spring knows, if we overstretch a spring, if we stretch it so far, you get to a point that when you take that force off, it does not return to its original length. What we've done is we've caused permanent, irreversible deformation of that spring, which is called plastic deformation. So Hooke's law is only valid for a displacement in the elastic region. If you overstretch your spring, this linear relationship is no longer true. If you get to the point where this displacement overstretches the spring, causing plastic deformation, it actually drops from linear and it begins to kind of flatten out like this. In which you continue to stretch the spring, but you don't get any additional force being pulled by the spring in that case. But we typically will design springs and systems such that they're not intended to go into that plastic deformation. So springs are generally designed such that they stay in that elastic region. Okay, let's work a simple Hooke's law example problem. So the problem reads, an unstretched spring with a spring constant of 75 newtons per meter is attached to a wall on the left and a movable block on the right. The block is moved from 0.2 meters to 0.3 meters from the wall. What is the spring force exerted on the block? Okay, so this is what this problem is starting with. So initially we have a block that has attached to a wall with a spring, and the spring has an unstretched length of 0.2 meters. Okay? Now, the spring was given to have a spring constant of 75 newtons per meter. So what happens now is we apply a force. We apply a force to this block. We apply some external force to this block, and it causes this spring to stretch. It stretches from 0.2 all the way out to 0.3 meters. The problem is asking, what is the force that is being exerted on the block by the spring? So if we're considering just the block, we have some externally applied force acting to the right, and then we have the force from the spring acting to the left, right? Because at this point, we have just pulled the block and stretched that spring, and now we're just holding that block where it is, so this block is kind of in equilibrium. But that doesn't really matter. The problem is just asking, what is the force of the spring on the block? For this, we just jump right into Hooke's law. So Hooke's law says that the force of our spring is going to be equal to negative K times L minus our natural length. So in this case, we say that our force of our spring is equal to negative. K was given as 75 newtons per meter, and we stretched it to a final length of 0.3 meters. minus its natural length, which was given at the beginning of the problem. Its natural length was 0.2 meters. So we end up with that the force of our spring is just 75 times 0.1, which is just a negative. Force of our spring is equal to a negative 7.5 newtons. Okay, now I want to be real kind of careful with how we consider these problems. It's really easy when you work Hooke's Law problems to get all bent out of shape about this negative sign out front. Okay, a lot of times it's almost easier to consider the magnitude of Hooke's Law. The magnitude of Hooke's Law, saying that the magnitude of the force is going to be equal to the magnitude times the spring constant times the length minus the change in length. All that negative indicates, that negative just indicates that it's back to the left. It means it's in the opposite direction as our change in, or our displacement. So our displacement was 3 minus 0.2, or was a displacement of 0.1 meters to the right. That just means that the force of the spring on the block is back to the left. It can be really easy to get confused with this negative sign. So a lot of times it'll be easier to just kind of consider the magnitude, and then just analytically, by analyzing the problem, you determine what direction the force should act. So we know if we just looked at this problem, if we just did it magnitude-wise, we would get that the force of our spring is going to be 7.5 newtons, or the magnitude of the force of our spring is going to be 7.5 newtons. And then just from looking at the problem, if I'm pulling to the right and I'm asking what the force of the spring on the block is, we can easily tell that it's to the left. So we can easily tell that it's to the left. This is just a valid way to solve this problem, as being really careful with your negative signs. I just want to make sure that everyone's clear. Don't get so worked up about the negative sign. Make sure that your answer makes sense. So when you step back and you look at your problem, make sure you understand what direction that spring force is acting. Okay, let's work a little bit more complex Hooke's Law problem. The problem reads, a 10 kilogram weight hangs from a spring. You measure the spring to be 22 centimeters long. You hang an additional 10 kilogram weight from the spring, and you measure it to be 24.4 centimeters long. What are the spring constant and the natural length of the spring? So, we initially have a spring, and we say that it has that we have 10 kilograms hanging from the end of the spring, and we measure it to be 22 centimeters long. Okay, we add that, we increase that mass to 20 kilograms, and now we have a 24.4 centimeter length that we were able to measure. So this problem is a little bit more complicated because I didn't give you the natural length of the spring. I didn't give you the natural length of the spring. When we said that Hooke's Law is that our spring force is equal to our spring constant times our length minus our natural length, right? So we need to know what our natural length is in order to solve these sort of problems for a spring force. So I worked this problem two different ways. I want to make sure that I kind of illustrate that you can use both those forms of Hooke's Law that we presented. So we presented this form of Hooke's Law the same, and then we said that because the relationship between the displacement and the spring force is linear, we can actually get rid of this natural length. And we also had the form of Hooke's Law in which we said that a change in the spring force is going to be equal to our spring constant times a change in displacement, So we're going to solve this problem using both these methods to kind of show you to illustrate how you can solve it using either way. Okay, so let's go ahead and solve it the first way first. Let's go ahead and solve it the first form of Hooke's Law first. So, the first thing that we need to recognize is we can say that if we're hanging a mass off of the spring, we know what the spring force is. So if I just draw kind of a general free body diagram of some mass m, it doesn't really matter. It has a weight of mg, and it has a spring force acting upward, right? So we know for equilibrium, if this mass is hanging stationary, that the spring force is going to be equal to our mass times our gravity. It's going to be equal to the weight of the mass. Okay, so we can say that in our first case, we're going to call this case 1 and case 2. in case 1, our spring force is going to be equal to mg. So our spring force is going to be equal to 10 kilograms times 9.8 meters per second squared. That is going to be our spring force, is going to be equal to, and I'm going to use, like we talked about in the previous problem, I'm just going to kind of solve this in magnitude form because it doesn't really matter. We know that our spring force is up. We know the magnitude of our spring force is going to be mass times gravity, so 10 times 9.8 meters per second. And we know that our spring constant, actually we don't know our spring constant, we're after that value. And then we're going to say that our length minus our natural length. So in state 1, our current length is going to be 22 centimeters minus the natural length, which we do not know. And the natural length is going to have some length less than 22 centimeters. So everything with our signs all kind of works itself out. 22 minus some number less than 22 is going to be a positive value. So this whole positive value is going to be equal to this whole positive value. So this is our state 1. This is our first state 1. So we can go ahead and say that this 10 times 9.8, I'm going to just go ahead and simplify that. This is going to be a 98 newtons. 98 newtons. Okay, we do the exact same thing for our state 2. Our state 2, now we've increased our mass to 20 kilograms. So we get a 20 times 9.8. It's going to be equal to the same spring constant, but now it's stretched to 24.4 centimeters minus the same natural length. Okay, what we end up with is if we say that this is 20 times 9.8, so this is going to be 196. 196 newtons. But now we have two equations with two unknowns. So we should be able to solve this system of equations. We should be able to solve the system of equations. We can say that this is 98, or this is the same spring constant and an unknown natural length, same spring constant and some unknown natural length, and we need to figure out some sort of method to solve this system of equations. Okay? Well, what I can recognize is because this is 196 and this is 98, right? We doubled the mass. If I multiply this entire equation by 2, I get that 196 is equal to 2k times 22 minus my natural length. Okay, 196, that's the 2 times this top equation. This bottom equation is also equal to 196, so I end up getting a k times 24.4 minus natural length. Now I have an equation. You think I have one equation with two unknowns, but luckily for me, because we were clever in how we solved this system of equations, now I have a k on the left and a k on the right, so my k's cancel out. So now we can say that this just becomes 2 times 22 is 44, minus 2 natural length is equal to 24.4 minus the natural length. So I can move this negative 2 natural length over to the other side of the equation. So I get that a, and I move my 24.4 over to this side of the equation. So I get a 44 minus 24.4 is equal to negative natural length plus 2 times the natural length. That tells us that the natural length is just 44 minus 24.4, which when I plug into my calculator, I get a 19.6. I get 19.6 centimeters. Now that I know my natural length is 19.6 centimeters, it doesn't matter which equation that we go back to. We can go back to equation 1, or we can go back to equation 2. So let's just go back to equation 1, and we just plug in that natural length value that we know, and now we can solve for our spring constant k. So 98 newtons is going to be equal to k times 22 minus 19.6. So now I know everything in this equation. 22 minus 19.6, I divide that both sides, and I get that my spring constant is 40.8 newtons per centimeter. 40.8 newtons per centimeter. I went ahead and kept everything in the kind of standard, or not the, I shouldn't say standard units, but I kept all my lengths in centimeters. It's very common when you buy springs from spring manufacturers that this is a kind of a standard unit. You see a lot of units where it's newtons per centimeter or newtons per millimeter, depending on what the actual displacement of the spring is designed to be. It doesn't make a lot of sense to sell springs where you rate them in newtons per meter if your spring is only going to stretch a couple millimeters at a time or a few centimeters at a time. So it's really common to have K values in the newton per centimeter, or the newtons per centimeter kind of form. Okay, so we were able to solve this equation, or this problem, for both our natural length and our spring constant, by using this form of Hooke's law, Hooke's law. We also introduced the other form of Hooke's law because Hooke's law is linear. Now I'm going to go ahead and just do it in the magnitude form because it makes it a little bit easier to not get confused with your signs. Is that some change in force is going to be equal to K times some change in length. That was the other form of Hooke's law that we could have chose to do. In this case, it makes this problem a lot easier to solve. So anytime that you don't know the natural length of your spring, this is a much simpler form to try and solve these equations in, because I can just say, okay, initially I had 98 newtons hanging from my spring, and then I went to 196. So I had some change. Of going to 196 from 98. So that's my change in my spring force, and my change in my spring force is going to be equal to some spring constant by some change in length. And my change in length in this case was from 22 to 24.4. So from 24.4 from 22. And I'm just making sure that they're in the same order, right? They're in the same order. So all I'm saying is that if I just want to do this in parentheses, that's fine, because this is going to be state 2 minus state 1, and this is going to be length 2 minus length 1. So this was my spring force in state 2. This is my spring force in state 1. This was my second length, and this is my first length. But this is a very, very simple problem. Now, this is much easier to solve, and then we can just directly go ahead and solve for K, and we would get the same answer. We get the same answer that K is 40.8 newtons per centimeter. 40.8 newtons per centimeter. Once we know what our spring constant is, we can pick either state. We can pick state 1 or state 2, and we can then use that to solve for our natural length. So we can say that if we go back to Hooke's law for just a simple state, we can say that our spring force for state 1 is going to be equal to K times L minus our natural length. So I get that my spring force in state 1 was 98 newtons, is equal to 40.8 newtons per centimeter. And then we're stretched to 22 from some natural length. Now this is a much easier problem to solve than what we solved last time. Once again, I'm down to one equation with one unknown. I can algebraically solve this, and I would get the exact same answer. I would get that my natural length is 19.6 centimeters. 19.6 centimeters. So often, if you're working a problem where you don't know what the natural length of your spring is, it's much easier to work in kind of your linear difference form. Your linear difference form, not going all the way back to your length minus your natural length. We can be interested in just a change in force and a change in length, and we can get the exact same answers. We do not have to use just one spring at a time. So the last kind of piece of information I want to cover in this chapter is what we call equivalent springs. So I can use multiple springs together combined into a spring system. In order to analyze systems of springs, what we do is we replace multiple springs with an equivalent spring. So we replace multiple springs with a single spring that has a different K value that would be equivalent to those multiple springs all working together. So there are two different configurations that we can combine springs in. We can combine springs in series, like shown right here, and that means stacking the springs end to end. They don't have to have the same K value. In fact, we're usually going to have different K values, but we call this adding springs together in series. The other way that we can arrange multiple springs is we can arrange them in parallel. And when we arrange them in parallel, we have them stacked like this, side by side. So if I want to replace these two springs in series with one spring that has an equivalent behavior or an equivalent K value, the equation to do that is given right here. 1 over my equivalent K value for my spring is going to be equal to 1 over K1 plus 1 over K2 plus however many springs that you have in series. Whereas if we have springs arranged in parallel, I would replace them with an equivalent spring where I'd have my equivalent K value is going to be K1 plus K2 plus however many springs that we have in parallel. So these are the equations for how we combine springs in series and parallel, but where did they come from? So let's think about where springs in series, or how springs in series behave. So if I have two springs in series like shown, and I apply a force to those springs, that force is continuous all the way through both of those springs. That means that the force, that spring 1 carries a force F and spring 2 carries a force F, so they both carry this same force. So if I wanted to figure out what the total elongation of the system would be, the total elongation of the system is going to be how much does spring 1 elongate plus how much does spring 2 elongate, which we can figure out from Hooke's law is just going to be F over K1 plus F over K2. In this case, I have F in both of these terms, so I can say my total elongation is F, which I factor out, and then I have 1 over K1 plus 1 over K2. If I wanted to get this back into standard Hooke's law form, which is F is equal to Kx, I have to divide both sides by this term. I have to divide both sides by this term, and what I get is I get that my force is going to be equal to 1 over this 1 over K1 plus 1 over K2 times my total displacement. So we figure out that our equivalent spring would have this entire term spring constant. It's going to be 1 over K1 plus 1 over K2, 1 over that entire value. So if we have more springs, you would do your summation of your inverses first, and then finally you take your inverse at the end. Now, for springs in parallel, if I apply a force to those springs, the relationship that we have to consider is that both springs are going to be displaced the same amount. Now, no longer will both springs carry the entire force F. In fact, some of that force will be carried by spring 1, and some of that force will be carried by spring 2. So we can say that the total applied force is going to be the force that is carried by spring 1 plus the force that is carried by spring 2, which we can then replace these forces with Hooke's law, but once again, both of these springs will have to be stretched by the same amount. So we can replace them with K1 times that displacement plus K2 times that same displacement. Once again, I can factor this displacement out, and I get it into a form of Hooke's law that we are familiar with, in which I have the force is equal to some equivalent spring stiffness, some equivalent spring constant, times X. So this is kind of how we derived those two different formulas for springs in series and springs in parallel. Let's work a spring system example problem now. So the problem says that 4 springs are arranged as shown. How far will the 30-pound weight drop once attached as shown? So what we have here is we have a system of 4 springs. We have 4 springs arranged in this particular configuration, and then we're hanging a 30-pound mass. What we're really saying is we're just applying a 30-pound force downward at the bottom of these springs. So we're hanging a mass, we're applying a 30-pound force downward, and we're after how far this bottom, this displace when we apply that 30 pounds. Okay, so what you want to do anytime that you're working a combination of multiple spring problems is you have to break it up into steps. So we're saying that we can arrange springs in 2 different ways. We can arrange them in series or we can arrange them in parallel. So we want to find springs that we know to either be in parallel or we know to be in series. And once we know that, we're going to combine those, or we're going to replace those 2 springs with an equivalent spring. So for example here, when I look up, my first springs that I see K1 or spring 1, which has a spring constant of 30 pounds per inch, and I have spring 3, which has a spring constant of 20 pounds per inch. These 2 springs are definitely in parallel. These two springs are definitely in parallel, so I can replace them. So I can replace these two springs with an equivalent spring, which I'm going to call, is going to have a spring constant. I'm going to call it 1, 3, because I'm replacing spring 1 and spring 3 with an equivalent spring. And because they're in parallel, it's just K1 plus K3. We just add them directly, which makes sense, right? We have two springs. If I was to pull down right here, I would have to stretch both the springs together. That'll make the equivalent spring stiffer than either one of those springs. So we have that K1 3 is equal to 30 plus 20 is going to be equal to 50 pounds per inch. 50 pounds per inch. So once we do that, we go ahead and I go back to my diagram, and I like to redraw my diagram with the equivalent spring that we have just replaced two springs with. So we just replaced both these springs. Now we have a spring that has a spring constant, or equivalent spring that has a spring constant of 50 pounds per inch. Okay, now I look at this and I say, okay, I have this equivalent spring 1, 3, I have spring 2, and I have spring 4. This side and this side are in parallel, but it's kind of confusing. But what I can tell right away is that this spring, spring 1, 3, and spring 2 are definitely in series. They're definitely in series. They're one after the other. So I can then replace these two springs with an equivalent spring as well. So I can say that my 1 over K, and I'm going to have springs, or equivalent spring 1, 3, and spring 2. So I'm going to have spring 1, 3, 2. It's going to be equal to 1 over spring 1, 3 plus 1 over spring 2. This is going to be my equation for springs in series, and I know what all these values are. This is saying that I'm just going to rewrite this as K 1, 3, 2 is going to be equal to 1 over 1, 3 we just found to be 50, and 2 we know to be 60. Now I'm going to have to take the inverse of this entire thing to go ahead and solve that. I can plug all this into my calculator, and I get that my equivalent spring that replaces springs 1, 2, and 3 is in fact 27.3 pounds per inch. Pounds per inch. So I go back over to my problem and I say, okay, I just replaced this equivalent spring 1, 3 and spring 2 with a new equivalent spring. So now I have an equivalent spring K1, 3, 2, which we found to be 27.3 pounds per inch. Finally, we got down to this point, we can see that this equivalent spring and spring 4 are definitely in parallel. They're definitely in parallel. So now I can replace it one more time with an equivalent spring. So we can say that our equivalent spring for all four, so K1, 2, 3, 4, is just going to be equal to K1, 3, 2 plus K4 because they are in parallel. So that means that K1, 2, 3, 4 is equal to 27.3 plus 40 is equal to 67.3 pounds per inch. So now I go all the way back to my original problem. I replace these springs one more time. Now I just have a single spring, which I'll just call it KEQ, or equivalent spring, which has a magnitude of 67.3 pounds per inch. Okay, so it was 3 steps. We had to replace springs in 3 steps, but now we have an equivalent system, or an equivalent single spring system. So if we were to replace all 4 of those springs with a single spring that had this spring constant, it would behave the same way. So that's what we're after here. So we had 4 springs arranged in a complex configuration. We have figured out what spring we could replace all 4 of those springs with and have it behave the same way. Once we have a single Once we have a single spring with a single spring constant, this becomes a simple Hooke's law problem. This becomes a simple Hooke's law problem. We have that our spring force is equal to K delta X, so this is going to be some change in length that we're after, and we know that this is going to be 30 pounds, is going to be equal to 67.3 pounds per inch. And then we're going to have some change in X that we don't know. So we divide both sides by 67.3, and we get some change in X or some change in Y, whatever you want to define your axes to be. I'm calling it X in this case. So in this case, I'm defining my positive X direction to be this way. My delta X is going to be 0.446. 0.446 inches. So from that complex spring system that we started out with, we ended up with we ended up with an equivalent system of only one spring, and if we apply a 30-pound force to it, we stretch that equivalent spring 0.446 inches, which is exactly what would happen if we applied that 30 pounds to that system of springs. That 30-pound weight would then displace downward 0.446 inches. Okay, that is where we are going to end the lecture for today. So we just covered Chapter 5. So Chapter 5 is not going to be on your Exam 1. So that's what I wanted to remind you about, is do not forget, while I am out of town this week, I posted this video lecture to cover Chapter 5. You also have a Chapter 5 homework due next week, but throughout this entire week in the Math Testing Center, you are available to take Exam 1, and Exam 1 covers chapters 1 through 4. So please do not forget to take your Exam 1 sometime this week in the Math Testing Center, and do not forget that this Chapter 5 homework will still be due next week. So you have two big assignments. You had Chapter 4 homework due on Tuesday. You have the lecture for Chapter 5 that you have to watch. You're going to have Chapter 5 homework due next Tuesday, and you also have to take your exam sometime this week in the Math Testing Center. So please do not forget to do all those things. I will see you when I get back. Good luck to you.